morning everyone. I am Engineer Misha, Chairperson CRD, and today I am excited to share our work on spectral analysis of lung sounds for classification of asthma and pneumonia wheezing. We will look at how we can use signal processing and machine learning to bring low cost, accurate respiratory diagnostics to the field, potentially where medical expertise or expensive imaging isn't available. Here's a shocking fact: lung diseases are still one of the world's top killers. Asthma alone affects over 235 million people, and pneumonia, well, it takes around 3 million lives every single year. Now, one of the key signs doctors listen for is something called wheezing. And wheezing, that high pitched whistling sound when you breathe. It's like your lungs are trying to play the flute, but it's not music you want to hear. And what's the problem? Well, the problem is detecting wheezing accurately needs trained ears, quiet conditions, and expensive equipment. That means millions of people might not get diagnosed early enough. So, here's the idea we had: what if we could teach a computer to listen for us? We record lung sounds, run them through something called spectral analysis, basically turning sound into data, and then use machine learning to classify whether it's normal breathing, asthma wheeze, or pneumonia wheeze. Sounds futuristic, right? Well, we have actually built it, and in this video I'm going to show you how it works, what we discovered, and why this could change respiratory care forever. So here's the mission. We wanted to build an AI that could listen to your lungs and instantly tell, is there normal breathing, is it asthma wheeze, or is it pneumonia wheeze? To pull it off, we use something called spectral analysis, basically turning lung sounds into a visual map of frequencies, and then trained to a support vector machine, SVM, or you can say that a machine learning algorithm to spot the differences. And what were our targets? Pinpoint accuracy, lightweight processing, so it can run on basic hardware, and most importantly, make it cheap enough to fit into a portable device. Why? Because if we can put this tech in the hands of frontline health workers, we can bring early lung disease detection to places that have no specialist doctors at all. Now, I will be honest, we are not the first ones to try teaching a computer to listen to lungs. People have tried using MFCC with SVM, FPGA based hardware, even neural networks. Well, here's the catch: wheezing is tricky. It doesn't sound the same every time. It can blend in with your heart sounds, and in real life, there is always background noise. Imagine trying to diagnose someone's breathing while standing next to a busy street. Our mission was to build something more robust, a spectral based system that could still deliver high accuracy without needing bulky, expensive hardware to run on it. So, our pipeline follows four main stages: data acquisition, preprocessing, feature extraction, classification. The idea is to first clean and prepare the lung sound signals, extract meaningful spectral features, and then feed them into our chosen classifiers. So, how do we actually teach an AI to listen to lungs? Our process follows four main stages. Step 1: data acquisition. We record lung sounds, actually real lung sounds from patients. Step 2: preprocessing. We clean up the audio, remove noise, and isolate the important parts. Step 3: feature extraction. We break the sound down into spectral fingerprints, that is, unique patterns that tell us what's really going on. Step 4: classification. We need those patterns into our classifier to decide, is it normal breathing, asthma wheeze, or pneumonia wheeze. It's basically record and clean and understand and then decide. Simple in concept, but it took a lot of work to get it right. We collected data at Pakistan Institute of Medical Sciences, PIMS, Islamabad. We had 300 subjects, 100 asthma, 100 pneumonia, and 100 normal. 10 recordings per subject, each 10 seconds long, were done. We used an electron microphone, a stethoscope, filter, and an amplifier for quality capture. And these signals were mostly taken from nostrils or right lung areas for the best sound clarity. So this is basically, as you can see, the data acquisition process for the breathing sounds. The first one is the lung sound, where you have an electronic mic and a mouthpiece. Then we have a sound recording block, which contains a card reader. And then obviously once you have recorded the data, then you try to import it. And initially we try to store these lung sounds in our laptop in .wav form. And below you can see the details of the acquired samples, the classes, the gender, the age range, and the number of samples collected for each class. Alright, let's be real. Raw lung sound recordings are messy. You have got background heart sounds, hums, silence, random noises, not exactly air friendly, right? So first we run normalization using min-max scaling to make sure all recordings are on the same amplitude scale from 0 to 1. Then the next step is segmentation. We slice these audios into tiny 250 millisecond frames. That lets us throw away silent or non-breathing parts. Finally, filtering. We use a 10th order Butterworth bandpass filter focusing only on the 250 Hz to 2K Hz range, right where he sounds like to live. The result? A clean, clear signal that's ready for feature extraction and a much happier AI. So here's what our lung sound looks like before preprocessing. That is noisy and inconsistent. And after preprocessing, if you see that, it's much cleaner with the wheeze components clearly isolated, or at least they are potentially separable now. Once the lung sounds are clean, it's time to turn them into data the AI can understand. We extract 9 spectral features: centroid, crust, decrease, entropy, flatness, flux, roll-off, slope, and spread. And another question is, what do these actually mean? Well, they describe things like where most of the sound's energy sits, how sharp or peaky it is, how peaky it drops off, and how wide basically the frequency range is. Well, you can think of it like making a fingerprint for each lung sound. Asthma wheeze, pneumonia wheeze, and normal breathing each leave their own unique pattern, and that's what our AI learns to recognize. So these are basically the scatter plots of some of the extracted features, and this one in particular is of spectral centroid versus spectral crust. This is of spectral centroid versus spectral entropy. This particular graph is about against spectral centroid versus spectral flux, spectral centroid versus spectral roll-off point. And basically here you can see that these are, when you are talking about extracted features, they are basically some x and y coordinates in from perspective of graphical point of view. And here you can see the blue ones are the actually correcting asthma wheeze. This yellowish one is pneumonia wheeze, and if you see the normal one is actually quite scattered and it is of orange. So that's how the features are actually, if you draw them, then that's how they visually looks like. Now for the brains of the operation, the classifier. Well, we tested a bunch of options like linear discriminant, naive Bayes, variance, fine tree, different flavors of canon, and backtrace. But the real MVP, well, it was support vector machine known as SVM. We even put SVM through a mini tournament, like trying out linear, quadratic, cubic, and multiple Gaussian kernels. And guess what? Simple linear SVM came out on top, hitting 96.7% accuracy. And it's lightning fast, which is perfect for our final deployed low cost portable device based application. And here, how you can see accuracy comparisons. Well, not in this particular slide, in the next one I will show you the comparison. So but if here you see the comparison between kernel and classifiers, linear SVM consistently outperformed others, while other 96% accuracy in both 5-fold and 10-fold cross validation. And if you see, I will show you the confusion matrix in next slide. It shows only minor misclassifications between asthma and pneumonia wheezes, which is understandable given their acoustic similarity. Now let's talk numbers. Why? Because this is where it gets exciting. Because we put our system through multiple classifiers and the winner was crystal clear. Linear SVM, as here you can see, with a begrudging, not begrudging, well, very good accuracy of 96.7% accuracy. And other SVM kernels, the quadratic one, cubic, Gaussian, well, they came close, but nothing topped the simple linear approach. Even when we did cross validation, that is, we did actually both 5-fold and 10-fold, the accuracy stays rock solid at around 96%. And if you look at the confusion matrix, you will see only tiny misclassifications, like 3% of asthma is mistaken for pneumonia and 4% the other way around. That's big deal because it means our system isn't just accurate, it's consistent, and that's what you want in a medical tool. So here's the takeaway. Combining spectral analysis with machine learning algorithm, and in particular, in specifically in our case, SVM, turns out to be a powerful way to classify these types. We are talking high accuracy, computational cost, and a system that could realistically fit into a low cost portable device. Imagine health workers in remote areas using something like this on a simple handheld tool. And we're not stopping here. Next up, building this into hardware, testing it with larger and more diverse datasets, and basically expanding it to detect other lung sound conditions. And what is the goal? What is CRD aiming to get? To make AI powered lung health diagnostics available to everyone, everywhere, all around the globe, and that too free of cost. Well, alright, before we wrap up things up, let's talk about what's next. And I had love to hear your thoughts in the comments. And the first big question is, what if we combine spectral features with time domain features? Could that give our system an extra accuracy boost? Think of it like giving AI two different camera angles of the same event. Second, real world testing. Hospitals are not quiet. There's coughing, talking, and a whole orchestra of background noises. How well would this particular system perform in that kind of chaos? And the third is, could deep learning outshine our trusty SVM? Neural networks have been making headlines, so maybe they could pick up patterns we are missing right now. And finally, what about kids and elderly patients? Their lung sounds can be very different. Should we train separate models for different age groups? Or we can make one model that adapts to everyone. So what do you think? Drop your ideas in the comments, and if you enjoyed this deep dive into AI powered healthcare, hit that button, subscribe for more, and I will see you in the next video.